Chemical properties of ethers. Basic character. Due to the presence of lone pair electrons on oxygen atom, ethers are Lewis bases. They can form stable addition products with Lewis acids like boron trifluoride, anhydrous aluminum chloride, etc. For example, diethyl ether forms an addition product with boron trifluoride. One of the lone pair electron is donated to boron. This addition product can be written as CH3, CH2, twice oxygen dot BF3. This reaction is similar to reaction between ammonia and BF3 to form addition product NH3 dot BF3. Second, cleavage of ethers. Ethers can be decomposed by heating with concentrated HI at about 373 Kelvin or by concentrated HBr under high temperature above 150 degree Celsius and under pressure 2 to 3 atmospheres. HCl and HF do not give this reaction. The nature of products formed depends upon the amount of hydrogen halide used, as well as nature of groups bonded to oxygen atom. The mechanism of cleavage may be either SN2 or SN1. That also depends on the nature of groups bonded to oxygen atom. Consider an unsymmetrical ether ROR'. Since HI, HBr, etc. are very strong acids, first of all, ether is protonated. By the acid to form protonated ether. If R and R' are methyl groups or primary alkyl groups, the cleavage follows SN2 mechanism. The bulky iodide ion, that is nucleophile, approaches least hindered carbon atom, that is the smallest alkyl group. Simultaneously, carbon-oxygen bond undergoes cleavage to form a mixture of alcohol and alkyl iodide. This is a SN2 process. Bond making and bond breaking take place simultaneously. If both R and R' are primary alkyl groups, or secondary alkyl groups or a methyl group, the mechanism follows SN2. Iodide ion approaches lowest alkyl group or smallest alkyl group to form an alkyl iodide. Simultaneously, an alcohol is also formed. Alcohol is a leaving group in this reaction. If R or R dash is a methyl group, methyl iodide will be one of the product. If R or R dash is a tertiary alkyl group or a benzylic group or an allylic group, the mechanism of cleavage follows SN1 mechanism. Suppose R dash is a tertiary alkyl or a benzylic group or an allylic group, then protonated either dissociate to form stable carbocation intermediate, tertiary alkyl or benzyl or allyl carbocation. In the next step, this carbocation combines with a nucleophile iodide ion to form R dash I. That is, if R or R dash is a tertiary alkyl group or a benzylic or allylic group, tertiary alkyl iodide and an alcohol, or benzylic iodide and an alcohol, or allylic iodide and an alcohol are obtained. If excess of hydrogen iodide is used, then the alcohol formed will further react with HI to form corresponding alkyl iodide. That is, nature of product formed depends upon the amount of HI used in the reaction. Mechanism of cleavage depends upon the nature of groups bonded to oxygen atom. The cleavage reactions of ethers can be classified into following types. Symmetrical ethers having alkyl groups bonded to oxygen atom. On treating with one equivalent of symmetrical ethers having alkyl groups bonded to oxygen atom, on treating with one equivalent or 1 mole of concentrated HI, the product obtained will be a mixture of alcohol and alkyl iodide. Alcohol and alkyl iodide are obtained. In this reaction, one of the carbon-oxygen bond in the ether undergoes cleavage. Symmetrical ethers having an alkyl group can be represented as ROR when it is treated with HI. One of the carbon-oxygen bond undergoes cleavage. The product is a mixture of alcohol and alkyl iodide. In this reaction, one of the carbon-oxygen bond undergoes cleavage. One of the bond undergoes cleavage. The product is a mixture of alkyl iodide and alcohol. Second, if symmetrical ethers having alkyl groups is treated with 2 equivalent or 2 moles of concentrated HI. alkyl iodide is obtained. In this reaction, both carbon-oxygen bond in the ether undergo cleavage. So the product is alkyl iodide. Thus, the nature of products depends upon the amount of concentrated HI used in the reaction.